So for our first set of examples and applications, we'll return to graphs. It'll be a little more sketchy in this part. So let's again fix, remember we have a graph gamma, which is has a set of edges and a set of vertices. The edges are not the edges in the usual geometric sense, but rather pairs of edges which are related by an involution which flips the orientation. So they are oriented edges. Okay, so given this context, we'll say that an edge path is a sequence of edges En. They need not be distinct, but where Ej is in E, such that for all I, the terminal vertex of Ei is the initial vertex of Ei plus 1. Of course, for all I where it's applicable, and this is, we say this is from the initial vertex of the first guy, E1, and to the terminal vertex of En. Okay. If one had to study graphs more fully, you would define this with a little bit of more care, because what you want to say is that given a vertex, we want to think of the single vertex also as an edge path, but that won't matter in our context, so we'll just take it as a sequence of edges, and we'll just assume this sequence is non-empty. If it's an empty sequence, we need extra data, which is a vertex, which is the initial and final vertex. Okay, so we can say an edge path is reduced. You can guess it. It's just that we don't have an edge and it's inverse. So that is, if Ei is not equal to Ei plus 1 bar for all I. Okay, so you don't have go somewhere and come back. And so these are the edges. Okay, so if you have any path, so given any edge path, there is a reduced edge path. So if I have an edge path from V to W, okay, there is a shorter reduced edge path from V to W. So if I had an edge path like this, then I could reduce it and go straight from V to W. Okay, but more significantly, given any continuous path, we can sketch the proof of the following. So the proposition, namely, any path which is from 0, 1 to mod gamma, geometric realization, such that the endpoints is a vertex and the final point also is a vertex, both endpoints are vertices, is homotopic to an edge path, and indeed to a reduced edge path. Okay, this statement is not quite accurate because an edge path is a combinatorial object, as is a reduced edge path, but these have geometric realizations. Namely, we saw already that each edge can be looked at as an edge in the other as a path, and you look at the star of these. These have geometric realizations. E1 star E2, and this is indeed a path from the appropriate initial vertex to the appropriate terminal vertex. Okay, so if I have any edge path, this is homotopic to a reduced edge path. This will be useful in motivating homology as well. Okay, so I shouldn't even say proof, I should just say idea of proof. Okay, I will be very sketchy. Remember each vertex. Okay, so it may be time to have a graph here. We have been talking in vacuum so far. So here we go. Here we have a graph, maybe with another thing this way and this way. Okay. So idea of proof is, remember each vertex has an open star around it, which is the interiors of all edges containing the vertex plus the vertex itself. Okay. So use Lebesgue number theorem as usual with respect to the star of vertices, so open star of each vertices. What by this I mean, of course, I take the inverse image under gamma of these, that's an open cover, divide these, and so then your gamma gets divided into segments. Okay, so gamma is going to be gamma 1 up to gamma n, Each one is contained in, each of these segments is contained in the star of a vertex. Okay. So far so good. What we have is that every time two stars intersect, we have an edge. So now we have a path, each segment is joining two vertices, and it's contained completely inside a star. Okay. And suppose this is V and this is W. Okay, this is contained in the star of, the segment here is contained in both star of V and the star of W. Okay, and so it's contained in the star of the edge, if you wish, the span of the edge, and inside that you can homotop it to the edge joining V and W. So if I have a pair of points and an edge joining that, open star of that, you can homotop it to the edge joining V and W. By the way, V may be equal to W, in which case it gets homotopped to a loop which has the star. So this was a quick sketch of the proof that paths are actually just edge paths. So immediate corollary to this is that mod gamma is connected if and only if for all V W in the vertices set of gamma and V is not W, there exists a reduced path from V to W. Now if, as I said, we had defined things more carefully, so single vertices are also reduced path, we don't need this V is not equal to W, which would be more convenient for applications. That for present purposes this is good enough. If there exists a if there exists a reduced edge path, and it's also equivalent to there exists a reduced just an edge path. Okay, so an edge loop is an edge path from V to V. Okay, V and V of gamma. Now we really want it to be non-empty. Even if we allowed a single vertex to be a reduced edge path, we don't want to think of this as a loop. So this is just a loop. And a reduced edge loop is of course a reduced edge path, which it's an edge loop which also happens to be reduced. Okay, so now this will let us look at our main concept, so which is a tree, which will help us here. So a tree T is a graph, so it's a non-empty graph with, let's just say, vertices non-empty. We don't want empty set to be the tree, such that for all V W in vertex set of T with V not equal to W, there exists a unique reduced edge path. From V to W. Okay, the existence tells you these are connected as topological spaces. The uniqueness will tell us more. They are contractible. That is the main topic we have to see. But I'll just state a proof, which is a proposition which is actually quite easy and purely combinatorial. So I won't say anything about its proof. So T is a tree. So a graph is a tree is equivalent to T is connected and has no reduced edge loops. So being connected will tell you there is always an edge path, and you can always reduce it to a reduced edge path. But you want to show there's a unique reduced edge path, so you can trade off between, so an edge loop will give you a non-unique reduced edge path from a vertex to itself, and so here really one has to be careful in terms of allowing constant paths as reduced paths. Okay, but anyway, so this is a digression. Now our main result, which will be the next segment, is to show that any tree has its geometric realization actually be contractible.